SwayamPrabha. Digital India. Educated India.
Okay, welcome back. So in this lecture, we're going to look at develop specific ways to find out the properties which are not directly calculated or directly measurable in experiments. Now, in principle, for a simple compressible systems, two particular intensive variable can define the properties. So theoretically, we should be able to calculate all properties such as U, H, entropy by just providing these two intensive variable. Okay, we can try to develop this relation in order to reflect the changes in the variables such as U or such as your entropy in some measurable variables such as changes in the pressure with respect to temperature, volume with respect to temperature, or in other words using the PVT relations which we can develop or measure in experiments. Okay, so our interest is to calculate the changes in, let's say, U, H, S, which requires a relation between variables. Okay, now remember these are not directly measurable. Okay, so what we can do measure is nothing but CP, CV and other relations related to. Okay, so all related to this we can calculate. Now let's try to develop general relations which involves specific heat. Okay, so let me try with the internal energy. Okay, so internal energy, let me say we are interested in variables TV. So we can write in differential form du as del U by del T V dt plus and thus I can write this as CV, which we know, and this is your del U by del V T dV. Okay, so similarly I can also express entropy two independent variables TV, okay, as follows. Now what we are interested is to represent this in a different way. Of course we know del S by del T V, which we connect to heat capacity, okay, which we know, okay, that is your nothing but your CV by T. Okay, but what about this? Okay, so here we are going to make use of Maxwell relations. Okay, so we also know that du is your TdS minus PdV. So let me make use of ds directly here because our interest was to calculate first U, change in U. So this I can make use of ds. So this becomes your T ds by dt V dt, and V is common here, so we'll use this T del S by del T minus P dV. Okay, so this is something which I can write as CV T dt. Okay, and here at this point I am going to make use of Maxwell relation, which tells me that del S by del V at constant T is nothing but dP by dt at constant V, and thus following expression would be T del P by del T at constant V minus P dV. So this is nothing but your du. Okay, so it contains constant volume term here, and this will be your constant temperature term. Okay, so when you integrate this to get your change in internal energy, this is going to be your CV dt, which will be from T1 to T2, and this is going to be V1 to V2 T del P by del T V minus P dV. So here of course the initial state was T1V and we went to T2 V2. Okay. So similarly we can also calculate the change in enthalpy. What would be change in enthalpy? So we already know HTP. So dH is going to be del H by del T P okay. This is going to be Cp dt plus okay. Now here again we are going to make use of S as STP. Okay, we're going to make use of the differential form of entropy here. Okay, and we also know that your dH is nothing but TdS plus VdP. So though we have written here dH as in the form of these two terms which connect Cp and then the partial derivative of H. So this will be the path corresponds to constant pressure, this will be the path corresponding to constant temperature, and by taking two paths you can change state 1 to state 2 from T1 P1 to T2 P2. Okay, but we need this expression in order to get that. So let me try to first derive this. So ds is equal to STP, so we can get your ds is del S by del T P dt plus del S by del P. Okay, this is nothing but Cp by T, and this we are going to make use of Maxwell relation. This becomes del V by del T P dP. Okay, so you can use ds directly in this expression. Okay, and this ds would be your. So finally if we make use of this expression we get dH as and integrate it Cp dt plus integral of V minus this would be T times del V by del T P. Okay, and this integral will be from T1 to T2, this will be from P1 to P2. Okay, and this is going to be your delta H2 minus H1. So let us try to understand a bit how to make use of such an expression. Now let's consider this TS plot, okay, diagram, and we are going to consider isobars. Okay, so let's say this is here, and then you have this. Okay, so now what we are interested is going from 1 to somewhere here, let's say 2. Okay, you can take this path 1, so this here is 1 and this is 2, and you can take its path from 1 to, let's say this is x at a constant temperature, then you are here constant pressure. So this will be the path, let's say 1x2. 1x is a constant or isothermal, and x22 is isobaric. Okay, or you can do this exercise a different way, where you can take it to let's say y, where 1y is isobaric followed by isothermal. There are many possibilities one can think of. For the case of 1x2, this expression would be, because you remember this is at constant pressure, this term is useful for constant temperature, hence I can write H2 minus H1 as Tx T2 Cp dt plus your P1 Px, and of course this rest of the term. Okay, so the first one will be, you're taking a system from P1, okay, T1 to Px, whatever Px here is, and you have T1, and then you're taking this T1 to T2. Okay, naturally the Px in this case is P2 because of the isobar. Okay, so this is a way to make use of simple enthalpy change or internal energy change, and you can come up with this kind of changes using different reversible path, and this is one of the illustration which we used. But now I can make use of this kind of expression to explain a couple of things. Okay, for example, considering that what we have developed for the case of enthalpy, okay, we can directly use this expression for the case where delta H is 0, and this would be the case for throttling process, which we have looked at earlier, where we have developed this expression that if you have T and P, then for a throttling system, okay, with the throttle here, for given P1 and T1, you can vary the property of the throttling valve, and you can change your PT, and this is an example of the inversion curve which you get. Okay, and this inversion curve, you can have different initial condition and you will get different kind of curves, and the maximum you can connect to obtain, okay, something like this. So this will be your inversion line, okay, and this will be the temperature which at the end of this curve will be your maximum inversion temperature. Okay, so we in the earlier discussion we have already discussed Joule-Thomson coefficient mu Jt, which is nothing but the change in temperature with respect to pressure at constant H. Now considering that your delta H is going to be 0 because H is constant, you can use the expression derived earlier and the following, which can come up with, okay, Cp dt plus V. Okay, so considering dH is equal to 0, so your mu Jt, which is going to be del T by del P, is nothing but minus Cp V minus T del V by del T at constant P. Okay, alright, so this is your simple Joule-Thomson coefficient relation, which can be evaluated using Cp and PVT relations. Okay, now we will take a look at how to calculate entropy change. Okay, so let us consider S as a function of T and P, and this we can write as a in terms of partial derivatives, del S by del P dt plus okay, and this we already know, this is nothing but your Cp by T dt. Now here we have to make use of Maxwell relation. So Maxwell relation tells us that del S by del P at constant T is minus del V by del T at constant P. Okay, the other thing which we are going to also define here is coefficient of thermal expansion, which is 1 by V del V by del T at constant pressure, and alpha, which is isothermal compressibility. And this will be your minus 1 by V del V by del P at constant T. So we are going to make use of these relations, Maxwell relation, and these two variables which we have defined, which depends on the changes in the volume with respect to temperature or with respect to the pressure. Okay, so this term is now can be written in terms of del V by del T P dP. Okay, and this is nothing but can be connected to the coefficient of thermal expansion here. So I can write this ds as Cpt dt minus beta V dt. So you can integrate now. Okay, so this is the way of calculating the entropy, which we defined as the intensive variable T and P. Similarly, I can also derive an expression where S is function of T and V. Okay, So your ds is in terms of partial derivatives. This is nothing but your Cv by T dt. And what about this? And based on the Maxwell relation, this is nothing but your dP by dt at constant volume. This is from Maxwell relation. So what we are interested is to connect this expression here in terms of either Cp or isothermal compressibility or your coefficient of thermal expansion. So we are going to make use of cyclic relation here. Cyclic relation can be written in this way for PTV variables. Okay, so I can get this in terms of these terms, and note that this connects the change in the volume with respect to temperature, and this connects the change in the volume with respect to pressure, and thus we can connect these two variables to isothermal compressibility or the beta coefficient of thermal expansion. So I can write this ds as Cvt dt minus 1 by del T by del V P T. I can take this here in the numerator, okay, and this can be written as further as the following. If I take it in the numerator, I can represent this in terms of your beta V, okay, and the denominator would be in terms of alpha, okay. So this becomes nothing but we'll get plus V beta V alpha dV or Cvt dt plus beta, okay. Thus you can get your S2 minus S1 as T1 T2 Cvt dt. Okay, so this was an exercise of getting the entropy change by two different paths by using two different combination of intensity variable. So let me just try to do more of exercise making use of Maxwell relation, and here what we are going to do is we are going to calculate the difference in the heat capacities, that is Cp minus Cv, okay. So let me start with here. So this is to evaluate difference in Cp and Cv. Okay, so let me start with this expression of TdS, which we know that it can be written as Cptt minus T del V by del T P dP, and this is Cp dt plus T okay dP dt constant volume multiplied by dV. So of course I can take the difference between these two, and if you take the difference, this will become, because the left hand side is 0, so this becomes Cp minus Cv dt, and this I can take it to the right hand side. This becomes T dP dt V dV plus T P dP, okay. Now I can divide this term here. I can get the following expression. Okay, so we have an expression of T as a function of V and P, okay. So in other words, I can now represent this T as a function of V and P. So I can take a differential of T. Now the reason which I am doing is to relate this partial derivative with this term. Okay, and this essentially means that this term is nothing but equal to this term, and similarly this term is nothing but equal to this term. So by comparing these two expression, okay, by comparing this expression with this one, so the A and B, let's say, so compare A and B, and both these expression will give us the same final expression of T. So let me just take one of them, T del P by del T V, Cp minus Cv is nothing but, okay, and this tells you that Cp Cv is nothing but T del P by del T, and using reciprocative relation I can get del V by del T P. Okay, so this is one expression which I got. Now here, in order for me to make use of coefficient of thermal expansion and isothermal compressibility, I would have to use cyclic relation. Okay, so let me make use of cyclic relation now. Cp minus Cv with cyclic relation of del P by del T at V as minus of del P by del Vt. So this is based on cyclic relation, and using this expression I can plug in back here, okay, and what I can get is the following: minus T del V by del T square at P and del P by del V at T. Okay, and this we can show that this is nothing but V T beta square by alpha. Okay, so beta we have already defined. Now alpha is thermal compressibility. Your del V by del P is always negative, and alpha is defined as minus 1 by V, so alpha is always greater than 0. But beta usually is positive but can be negative. For example, for water, beta is maximum at 4 degrees Celsius, but it is negative below 4 degrees Celsius. But beta square is going to be greater than 0. So with this particular term is going to be greater than or equal to 0. For the case where your beta is 0, this term is going to be 0. Okay, this can be 0 when temperature approaches 0 or beta is 0. Okay, otherwise positive. For the case of ideal gas, this is nothing but R. Okay, so with this, of course, we showed that Cp is of course greater than Cv with the formal expression. Okay, and I think what we went through this particular set of lectures is to find out the changes in the variables which are of interest, but they're not directly calculated or measurable from the experiment. But what we can do is we can make use of Cp, Cv and the PVT relations and the set of derivations which we did, and then making use of cyclic relation and Maxwell relation, we can calculate the changes in the desired thermodynamic properties. So with that, I'm going to end this particular lecture, and as well as this topic, we'll start a new topic in the next lecture.